what we have now is the application of inductors, which are electromagnets, into circuits. So let's review a little bit about how Faraday's laws and Lenz's laws work. So what happens is if you have, say, a magnetic field and it has some value and you have this loop, if there was no current in the loop and it was just a loop right here, a changing magnetic field strength would then cause a change in flux through the cross-sectional area of that loop. That would then induce an EMF that creates a current that opposes that increase because it's going to create a magnetic field. So that is going to oppose. So if this magnetic field through that one loop was increasing, then what's going to happen is it's going to induce a current, and then current is going to induce a magnetic field that will oppose that increase. So B induced would be in the opposite direction, and you would get a current through that loop. Okay? Now, that is kind of inductance that occurs like externally. So in this case, we're going to talk about mutual inductance. So basically, if you have two coils, and B1, coil 1 is going to be your source. So what happens is you have a current I going through solenoid 1 that looks like it is coming, what is that doing? Coming up over the back. So this is coming up over the top. So from back behind to the top. So it's creating a magnetic field to the right. So that is B of 1. Okay, that's the source. And that is passing through the cross-sectional area of loop 2, which itself does not have, it's not connected to anything. Okay, so let's say it's a wire here and it's not connected to a power supply. It's just a complete loop of wire. What happens is, if I were to increase the magnetic field through that first loop, so I could basically increase my current. If I increase current, that's going to increase B, which is going to increase the flux through loop 2, which is then going to induce a current that has to oppose the change. So if my magnetic field was increasing, I need B induced caused by loop 2 to be in the opposite direction. So there's going to be a current going through this loop that has to be in the opposite direction that's creating that. Well, then if you think about it, that magnetic field that is induced is now passing through solenoid 1, which is then going to create a change in flux through solenoid 1. And so that's going to induce an EMF that opposes the change as well. And so they're going to be influencing each other back and forth. This is what we call mutual inductance. Okay? So, we use the letter capital M for mutual inductance, and it basically tells us how much the flux to the second coil is caused by the current through the first. So that would be the flux through the second coil is being caused by the current through the first coil. So you could then solve for that flux, and it's going to be M times I1. And then, because we know that it's the rate of change of flux that causes our induced EMF, as that flux changes over time, your induced EMF with Faraday's law has a magnitude of d flux 2 dt, but d flux 2 dt is going to be d dt of m times I1. M is dependent, is a constant. It's dependent only on the physical characteristics of the solenoids. So that's going to get pulled out in front. So that's where we get that E is going to be M di1 dt. And that's the EMF through the second one. Okay. Adding in the sign for opposite, you're going to get negative for that. So like this one was just the magnitude. Okay, we would actually use Lenz's law to figure out the direction. So this mutual inductance is geometric, which means it's due only on the physical arrangement of those coils. There's no subscript on M because the effect on the two are equal, because it's caused by the arrangement of the system. The unit of inductance, so that's M, is going to be the Henry, which is a capital H. 1 Henry is the same thing as 1 volt times second per ampere. So we can have mutual inductance, and we can have changes in one solenoid create changes in the other solenoid and back and forth. But actually, you don't need a second solenoid for this to happen. So there is something called self-inductance. So basically, if I change the current through this solenoid, that magnetic field that it is producing is creating its own flux. So this is the flux caused by its own magnetic field. So you don't need a second one. So if I increase the current that is coming into that solenoid, that is going to increase the magnetic field, which is going to increase the flux, which is then going to induce an EMF that opposes the change. So you're still going to get a B induced in the opposite direction, which means you're going to get a back EMF that is going to try and oppose that, and you're going to get an induced current that opposes that as well. If your current is constant, then it doesn't matter. The coil acts like an ordinary wire. But if the current is changing, then you're going to get a change in flux, and there will be this induced EMF. And then Lenz's law tells us that that must be in the opposite direction to oppose the change. So we define self-inductance as a capital I, okay? And this can be through any component. We represent them kind of like solenoids because that's what we traditionally think of. But it's going to be the magnetic flux over current. So you can then rearrange that and find that the magnetic flux is L times I. And therefore, if you want to once again do Faraday's law, where the magnitude of E is going to be the change in flux over the change in time, we get the magnitude of E is going to be d dt of L times I. L is also going to be geometric. It's based on the physical construction of the component. So our induced EMF is going to be L di dt. And then the negative, once again, comes because it has to oppose the change. So what's interesting is this is based on the rate of change of current over time. So if you were to think of a graph of current over time, and if my current is constant, then this is the slope of the graph. So that would mean that my induced EMF is 0 because the slope would be 0. But if, say, my current was, say, increasing over time, then the slope of this graph would be E. And you would have this induced EMF as that current is changing. And you don't, but that would be a constant EMF. But we could even have situations where, like, the EMF, the current reaches that asymptote. We saw this with capacitors, right? If you have an asymptote, then that slope is going to be changing at every instant. And so that means that our induced EMF is going to be changing at every instant. So the steeper the slope of that graph, the bigger the rate of change of di dt, the more EMF is going to be induced. Because it opposes the change, we call it a back EMF because it will be in the opposite direction. And anytime we now refer to inductance, we're talking about self-inductance, because that's the way we're going to use it in circuits. So the physical variable L, okay, is going to be dependent on the device. If our device is a solenoid, for example, the magnetic field created by a solenoid is mu naught Ni. Remember, Ni is your turn N is your turn density. Mu naught is your constant for free space, and then I is your current that is flowing through the wire. Okay, our flux, magnetic flux, is B times A. So you would do mu naught Nia, where A is the cross-sectional area of the coil. Now, if you have multiple loops, basically that flux is based on the sum of all of those, because you're going to have magnetic field passing through every single loop. So that is going to be N times D, where that is going to be your turn density, and D is going to be the length of that solenoid. They're not using L for length because we're using L for inductance. So D is going to be the length of the solenoid when you see that D. So you get that the flux is mu naught N squared Ia times D. So then to get inductance, you divide the flux by I, so that basically cancels out the current I, which makes sense because it's dependent only on the physical shape. So this is the cross-sectional area. This is the turn density. And this is our permittivity of free space. So that's if there's a vacuum inside of your solenoid. So what's kind of cool when you start looking at electrical components, if you find inductors, which are electromagnets in circuits, usually the inductors are wrapped around actually a piece of magnetized iron. So you've got basically your magnet here, and then you've got your wire loops wrapped around it. And then there's going to be your leads that come out. That's going to be what our inductors look like, our electromagnets in circuits. So why do they put a magnet inside? They put a magnet inside because basically this mu naught is for free space. If we actually used mu, that would be basically some multiplier, let's just call it K, times mu naught. So this is going to be some sort of constant. I don't remember what variable they use, but it's kind of like the dielectric constant. So the idea is the more ferromagnetic your material, the core, we call it the core of the solenoid, the larger mu. So I feel like iron is like 300 times the permittivity of free space. So you would get 300 times the inductive effect. So coiled wire gets really big. So if you want to try and make that inductor smaller, you need to put a more ferromagnetic material inside. If you got like a neodymium magnet and put it inside that inductor, that'd be a really, really strong inductor. So this is dependent only on the geometry. So it doesn't matter anything else. Just kind of the structure of that. All right, so what happens is that the inductors are going to change the way that current flows in the circuit. So if you were to picture, kind of current as a function of time. If I have a power supply here, and I've got like a switch, and I've got a resistor, what I assume is that while that switch is open, I have absolutely no current. And then if I were to close that switch instantly, I should be able to have a current equal to E over R right after that. That's what it says. But the problem with this, as soon as I put an inductor into here, di dt is the slope of that graph. This jump right here is vertical. The slope of that vertical section is infinity. And there's no way that di dt can be infinite. So it's actually impossible that the current can actually go to maximum value instantaneously. Even if there's no solenoid, even if there's just a wire, because remember, a long straight wire creates a magnetic field. And we don't have infinitely thin wires. So there's going to be some cross-sectional area through the inside of that wire. So what ends up happening is you are going to get a back EMF. And so instead of increasing instantly, as soon as you close that switch, it's going to approach an asymptote at E over R. And what inhibits that current jump is actually that back EMF. So that's what we're going to see is going to happen. So our inductors are electromagnets that have inductance when you put them into circuits. And they're going to be represented with a symbol that basically looks like a curved wire. So that will be my inductor L, kind of like I have capacitors C and resistors R and EMF sources E. All right, so here we go. So we are going to start with an LR circuit. In the derivation packet in the lab, you're actually going to see LRC circuits and even an LC circuit, I think. So you can have any combination of resistors, inductors, and capacitors with our EMF sources. So we're going to start off with the most simplified version of that. So we're going to have a switch, and we're going to assume that while that switch is open, that absolutely no current can flow. So we've got E0 we're going to use for our EMF source because we can get a back EMF, so it can get a little complicated when you're kind of talking about what you're talking about. So we've got our inductor L and our resistor R. So then what's going to happen is we're going to close the switch. So the instant you close the switch, current is going to try and flow through that inductor, which is going to create a magnetic field. That magnetic field is going to create a back EMF that creates an induced current that actually opposes the current that would be caused if the inductor wasn't there. So EL, or sometimes you'll see it as VL, is the EMF or voltage, because EMF and voltage are basically equivalent statements, that is produced. And that's going to equal our negative L di dt. Our di dt is going to be the slope of that current graph. Okay? So as we have an increasing current, so if I is increasing, then di dt is positive. If I is decreasing, di dt is negative. Okay, so like if I was to suddenly open the switch again, I lose my power supply, creating that that EMF, and so my current would start to drop, in which case the sign of my EMF would actually flip. And then after a very, very long time, because that current starts flattening out, your induced EMF becomes zero as you approach that asymptote, because the slope approaches zero, so your induced EMF approaches zero for that inductor. Okay, and then so basically that EMF equals zero is your voltage drop, and so this basically, when current is steady, behaves like a wire. At t equals 0, as soon as that switch is closed, basically that inductor is going to be able to so fully block that EMF, because your slope is going to be really steep. At the very base start, you're going to get a really, really steep slope that basically this guy here at t equals 0 when switch is closed, it's going to act like act like an open switch. And no current will flow. So this is actually the exact opposite way that a capacitor behaves. When a capacitor is uncharged, it has V equals 0, and it acts like a wire. As you close the switch, you will basically be able to ignore the capacitor at t equals 0, and then as it starts to charge, its own voltage increases, which then causes the current to decrease over time. And then after a very, very long time, the capacitor then acts like an open circuit, and no current can flow through it. So the inductor behaves the opposite. At t equals 0, the back EMF stops current from flowing, so the current in this circuit is going to be 0. After a very, very long time, the EMF of the inductor is going to be 0, and so what ends up happening is our steady state current is just going to equal E over R, or in this case E0 over R, because we've got the two different EMFs going. So that's the biggest thing to remember, is the currents in the inductors behave the exact opposite at t equals 0 and t equals infinity. So what happens is that your current is going to start off as 0. It's going to approach that asymptote. As long as it's a simple series circuit, then that asymptote's going to be E over R, according to Ohm's law. If you've got other things going on in the circuit, it won't necessarily be E over R, but it will still approach an asymptote. Another really cool aspect of the inductor circuit here is that the inductors actually are used in surge protectors, because if you picture that you got a spike in current, if there was an inductor in the surge protector, it would resist that and actually serve to protect the circuit and allow the current to come back up more slowly instead of spiking. So those inductors really, really come in handy because of this resistance. You probably think, well, why would I want to resist current? And that's because a lot of our components are sensitive. And if you increase your current too rapidly, you can cause components to burn out because there would be too much heat going through them, and that could damage the sensitive equipment. So by having the inductors in the circuit, they act as kind of a buffer to those electric jolts, thereby protecting your sensitive components. You are still going to have a time constant. That time constant for an inductor circuit is L over R. So that tells you the bigger the inductance, the longer it's going to take to get to steady state. And that's because it's going to be providing more back EMF. It's going to be better at resisting. The more actual resistance in the circuit, the smaller, the shorter time it takes. And that's because your current is going to be as large. So that slope, dIdt is not going to be as large. So you're going to have less of a back EMF, so it's going to be easier for the circuit to reach steady state. So, and once again, you could see that when you have one time constant here, that is going to be 63% of your max current, okay? And that you're going to reach steady state after about 4 to 5 time constants. So how do you use this in circuit? So we've been adding on to our loop rule kind of chart here. So you have to be a little careful. So remember, our capacitor charging was kind of this guy right here. Our inductors are going to behave differently depending on whether current is increasing or decreasing. So when current is increasing, then your dIdt is positive. So we actually don't change our function when we are working with inductors. But if our current is increasing, what ends up happening is dIdt is positive. And then when your inductance, L is always positive. So what you end up getting is negative times a positive. So that tells us that the term for the voltage is negative. So our voltage term is negative here. So it acts like a voltage drop when current is increasing. And then your induced current is going to oppose the original direction of current. Now, if, say, current was flowing and then we turn off the power supply, instead of the power supply dropping instantly to 0, what's going to end up happening is it's going to resist that change. And so it's going to end up falling slower and getting towards zero. So when doing instead of doing an instant drop, it's going to slow down over time. So if you think about it, if my current's decreasing over time, the flux through my solenoid is going to be decreasing. So I actually have to create a magnetic field that increases the flux, which means that my induced current is going to be in the same direction. It's going to try and help the current that was flowing through the circuit. So what happens though is di dt is going to be negative because the slope of this graph is negative. Okay, so my I versus t graph, the slope is negative. So di dt is negative, and then negative times the negative is positive. So the whole point is like that our voltage across that inductor is actually positive. So it's actually acting as the source. Acting as the source in that case. Over here, this is acting as a voltage drop. But you don't actually change what you write in the circuit. Okay, it's still negative L di dt every single time. When you do the capacitor, whether it's going the normal direction, the charging direction, or you're going opposite to the charging direction is going to determine whether it's a positive or a negative. So let's see how we can actually go about solving one of these loop rule problems for the inductors. And once again, this is a simple series circuit. We can see more complicated ones in the derivation packets. So we're going to choose a loop direction that is going to go this way around the loop. We're going to assume that at t equals 0, we are going to close the switch. So the initial current in the circuit is going to be 0. And then we're going to let the switch be closed for a really, really long time. So I'm not gonna use the E0 right now. We're just gonna use E. Because I'm gonna use just the equation straight up. So my voltage source is E. I'm gonna have a current through the resistor. And then I have negative L di dt. Like I said, you always use di dt is equal to 0, assuming you've got our travel direction for a loop is the same direction that the current is flowing. So we want to integrate in terms of I, so I'm going to need to set this up. So I'm going to add the L di dt term to the other side so that I get E minus IR is equal to L di dt. Now, kind of like I had to when doing the RC circuits, I'm going to do some manipulation that isn't strictly necessary for the calculus, but it helps me set up my equation so I get the expected expression in the way that makes most logical sense for analyzing the physics of the problem. So the first thing I'm going to do is I'm actually going to try and get that I by itself. Just by doing a little like fraction fun. So I'm not going to do fraction. I'm just going to multiply this whole equation on both sides by negative 1 over r. And I'm going to do that so I get I by itself. That'll make more sense later because I'm going to need to use that same natural log integral, so it'll help me out. Plus it'll help make some of the other terms make more sense. So that's going to give me negative E over r plus I is equal to negative L over R di dt. So one thing that I noticed straight out, part of the reason I wanted to do this is I've now discovered two really cool terms. The first term I've discovered is this one right here, E over R. If your potential difference across your inductor is 0, which is going to occur at steady states, then your inductor is going to act like a wire, and the current at steady state is going to be just what it was if the inductor wasn't there, and that is going to be E over R. So that's going to be that steady state current, that maximum current, if you want to call it a maximum current, once the current hits that asymptote. The other thing I want you to notice to find is by doing this, we actually discovered the time constant. Time constant tau is L over R. So part of that algebraic manipulation I just did is helping us to get physical meaning from our equation. So we don't actually need that right now. But what I'm going to do is I'm going to treat this term right here as its own whole thing. And I'm going to get everything that is related to I over on the other side, everything that's not related to I on the other side. So I'm going to multiply both sides by the negative r over L times dt. And then I'm going to divide the whole thing by I minus e over r. I'm just going to flip the order of that. Not super intuitive on how you do that, but it's the necessary steps to go about. So what that gives me over on the left is that's going to leave me with the negative r over L dt. On the right, that's going to give me di over I minus e over r. And now we're actually ready to integrate. So to integrate, we're going to start off with a current that equals 0, because at t equals 0, we have no current, and we are going to get our largest back EMF from that inductor, and so we're going to get an I induced that is equal to E over R, so that the overall current is 0. Okay, so there's going to be no current flowing at t equals 0 with that inductor. Full back EMF. And then it's going to go to I of t, because we're going to get that small trickle of current coming up and approaching that asymptote. And then our time's going to go from t equals 0 to t. So when we go through on the left side, we're going to get the negative r over L times time evaluated from 0 to t. And then on the right, that's going to be that same natural log. And because I've simplified this here, it's just natural log of the denominator. And that gets evaluated from 0 to I of t. Let me clear some space at the top. All right, so what we're going to do is we're going to come in and we are going to solve the left side. That's just going to be negative r over L times t minus negative r over L times 0. Always show your substitution. On the right side, we're going to get the natural log of I of t minus e over r minus the natural log of 0 minus e over r. Just like with the capacitors, reminders. Do not just this, it's not, you can't just say the second part of it 0, because it's not. So this left term has that canceling, so I get negative r over L times t is equal to the natural log of I of t minus e over r minus the natural log of negative e over r. Just like with capacitors, do not take the absolute value and get rid of that negative inside of there. Don't do it. We need to combine those terms first. So you get negative r over L times t is equal to the natural log of I of t minus e over r over negative e over r. So reminders, e over r is our I max. So I of t minus I max over negative I max is always actually going to be positive, because I of t has to be less than I max, so this numerator is always negative, the denominator is always negative. Actually, the numerator can be 0 at the asymptote, but you have a negative over negative, so that actually cancels out to a positive. So we do not need the absolute value here. So then the big issue is that we have the I of t still trapped in that natural log, so we take the exponential on both sides to undo the natural log. So I get e to the negative r over L times t is equal to I of t minus e over r over minus e over r. And then I can multiply by negative e over r on both sides, so I get negative e over r, e to the negative r over L times t is equal to I of t minus e over r. And then you can add that e of r to the other side, and so we get e over r minus e over r, e to the negative r over L times t is equal to I of t. So clearing space one more time. So we get I of t is equal to E over R times 1 minus e to the negative r over L times t. I guess that t got a little lost. So, a couple of things with this equation. So once again, this is I max in front. The reason I know it's I max is if t goes to infinity, e to the negative infinity is 0. So 1 minus 0 is 0. So I of t is just going to be equal to E of R. If I plug in t equals 0, e to the 0 is 1. 1 minus 1 is 0. So I at t equals 0 is 0. So this agrees with all of our assumptions for how the inductors behave. A little funky, we have R over L here. So the general equation for this, if you want to think about this, is I of t is equal to I max times 1 minus e to the negative t over tau. So, because this right here is actually 1 over tau, because it's reciprocal, because remember that tau is L over R. So that's kind of the general form of that equation. When you go and do this for basically decreasing current, so like if I was to reopen this switch and remove the EMF from this, you work through kind of in the same pattern, but this is for your I is increasing. When your I is decreasing, you're going to end up with your I of t being I max e to the negative t over tau. Okay, so it's going to do the opposite, because it's going to have to decrease from the maximum value towards 0 over time. So that's how you go through and you solve for the current. When you did capacitors, you had to do the differential equation to find charge first. When you do inductors, you do the differential equation to find current first. So you have to be careful with that. Additionally, what if you wanted to find some of the other values? So we know that current is dq dt. If you had a circuit that involved both inductors and capacitors, you might need to sub in dq dt in order to relate the charge to what's going on with the capacitor. If I wanted to find the voltage across my inductor, that's just going to be L di dt. Sorry. The magnitude is going to be L di dt. The voltage, that's going to be the voltage of the inductor. The voltage of the resistor is I times R. So you could plug your I of t into Ohm's law to find the voltage drop across the resistor over time. If you wanted to find the voltage across the inductor, you'd have to take the derivative of current over time to find that magnitude. Okay, so that's going to end up being a different calculation. So lots of different things that you can do with these circuits. So the last thing to talk about with inductors is going to be that these inductors are going to store energy. And they are storing energy in the magnetic field. So the potential energy that is stored in an inductor is 1/2 Li squared. So if you think about what's going on over time, is the current in that circuit is going to increase over time, and therefore as current increases, the potential energy stored in that inductor is going to increase. And this actually makes sense, because when you cut and open that switch with that resistor and that inductor, the current doesn't drop immediately. So if the power supply has been removed, how can there still be current going through this circuit? Well, it can still go through the circuit, because basically what happens is the inductor acts as the source with that induced EMF. Okay, so the inductor is going to act as a source, and so that potential energy is going to get converted into basically the kinetic energy of the moving charges and eventually get dissipated as heat. So that would be the amount of energy that you're stored in. Now, one other really cool application is, and you'll see this kind of in different points, is what happens if you, say, have a circuit that has both a capacitor and an inductor in it, something kind of like that. So basically what's going to happen is you've got a branch here. So let's say it looks like this. You're going to have current that is trying to go through both of those branches. Now remember that your capacitor, when it's uncharged, acts like a wire. And so what's going to happen is this is going to create a short circuit. So at t equals 0, all of your current is going to flow through that capacitor until it's fully charged, in which there'll be no current flowing through that capacitor. On the other hand, with your inductor at t equals 0, it's going to fully resist current, so no current's going to go through that, and then it's going to increase over time. So what you're going to see kind of in this circuit is what's coming out of your power supply is going to be kind of a little different, because it's got to be the sum of what's going on in your capacitor and your inductor. So there's going to be some initial current, and I'm going to use purple for my capacitor. So my capacitor is going to start off with all the current, and then it's going to decrease down to 0 when it's fully charged. I'm going to use blue for my inductor. So my inductor is going to start off with no current going through it, and it's going to increase towards an asymptote. And then what's actually going on in the circuit has to kind of be the sum of all of that. It may not be a perfectly flat line or anything like that in realistic. You just have to add up all the points. But they are doing the opposite, so theoretically it should kind of be the same. And so we should start off at steady state, and then we should kind of end at steady state. Assuming that, so let's actually, we need a resistor in there. Okay, so you got your resistor in there. Otherwise you're going to get a short circuit no matter what at the end. So we've got a resistor. So this could be like I through the resistor. Okay, it's going to be kind of steady. It's going to be the sum of that. And the purple is going to be for our inductor. Blue is the inductor. So that's going to be kind of fun. Well, what happens if you open a switch and you remove the power supply from that circuit? Well, what happens is our capacitors store energy. Our capacitors are 1/2 C times delta V squared for their potential energy. So the capacitor is going to be fully charged, and it's going to have all of this potential energy. And then what's going to happen is when you remove that power supply, that capacitor is going to start to discharge, and the inductor is going to resist that. And what's going to end up happening is the potential energy is going to go back and forth, because you're going to end up with your inductor having a maximum potential energy whenever the current is high, and your capacitor is going to have a maximum, the charge, it's going to be based on when its charge is maximum, because remember your delta V is Q times C, or Q over C. C is equal to Q over delta V. So delta V is Q over C. So we could replace this with 1/2 C times Q over C squared. So that gives us 1/2 CQ squared. Oh, nope, Q, what is that? 1/2 Q over C. There we go. That looks a little better. Q squared over C. Because they're going to have Q squared, C on the bottom. Yeah, okay. So you're going to end up with your potential energy in your capacitor being maximum whenever your charge is at a maximum. And so what's going to happen is you're going to end up creating an oscillating circuit where that current is going to end up flowing back and forth. It's going to keep changing directions as your inductor and your capacitor end up trading off as being the source of the EMF. So that's kind of cool. You kind of get an oscillator that way. So fun times when you start adding capacitors and inductors into circuits. If there was a resistor actually in that circuit, so let's say I had a resistor here, what would happen is your resistor would convert some of that potential energy into heat, that mechanical energy into heat. And so what would end up happening is you get a dampening circuit. And so you would end up with your values decreasing over time until it reaches kind of like a steady state. And then there would be no current flowing in. But if there's no resistance in that ideal LC circuit, that oscillation is just going to keep on continuing forever.